All right, so real quick recap of where we were in 3.5. We're looking at ratios of polynomials. Ratios of polynomials are called rational functions. We have vertical asymptotes, and vertical asymptotes occur when the denominator in its reduced form, the fraction has to be reduced, but if the fraction is reduced, it's places where the denominator equals 0. And vertical asymptotes always have an equation that says x equals a number. Horizontal asymptotes have one of three features. Either the degree on top is bigger, in which case there's not a horizontal asymptote. The degree on bottom is bigger, in which case the horizontal asymptote is y equals 0. Or if the degree on top and bottom are the same, we look at the leading coefficients, and it's the fraction created by those leading coefficients. So it's y equals that fraction. So the last one we had done that we were just talking about a moment ago was number 4. We had a degree on top and bottom that were the same, so we did a ratio of the coefficients, 2/1. Our denominator, our fraction that we were given actually was in reduced form, so our denominator equals 0 when x is equal to 1, so our vertical asymptote was at x equal 1. So we drew the dotted lines in that you see there in green there at x equal to 1 and y equal to 2. And then we had our x-intercept and our y-intercept that we found. Your x-intercept is when y equals 0, which is equivalently when the top is equal to 0. That gave us a value at x equal -2. And then we have our y-intercept, and our y-intercept is when x is equal to 0, which happened at -4. Once we did that, over here on the left-hand side, you'll see that we plotted those 2 points. Right, my white tip back on, right here and right here. And we can connect them. We have to connect them as they're moving toward the asymptotes. And then we needed an additional point up in the other side of the graph, basically bigger than x equal to 1. So we tried x equal to 2. And once we do that, we are able to sketch the right-hand side of the graph. All right, the next problem is a little bit different, and it introduces an asymptote that I haven't talked about before. So this one says final asymptotes and intercepts sketch the graph, just like the directions before. So we're going to look at the horizontal asymptotes, the vertical asymptotes, and go from there. Now, this actually has the degree on top bigger. We didn't have that one happen last time. What happens in that case is that there aren't any horizontal asymptotes. There's another kind of asymptote, and we are going to have to deal with it, but there's no horizontal ones. My vertical asymptote is when the denominator is equal to 0. The fraction is in reduced form. I can't factor anything in reduce. So the denominator is specifically equal to 0 when x is 0. Now, anytime you have the case where there are no horizontal asymptotes, what that's going to mean in the problems that we're encountering anyway is that there's going to be a slant asymptote. Now, in reality, a slant asymptote only occurs when the degree on top is 1 bigger than the degree on bottom. That's the only other kind that we're going to be presenting you with anyway. So let me talk about how we go about finding a slant asymptote. A slant asymptote is found by doing long division. Now, we haven't done long division with polynomials, so I want to walk you through that on this particular one. The denominator will go on the outside of the division. Remember long division from, grade school. Underneath the bar, you're going to put the numerator, but if there's any pieces that are missing, which there is right now, there's not a 0x, right? There's no x term, so I need to write in 0x, and then I have -1. Okay, so far so good? And we're going to ask ourselves a question something like this. Either you can say, how many times does x go into x squared? Or a better question I think that's easier to work with is, what do I have to multiply the x on the outside by to get x squared? Well, I have to multiply it by x. X times x is x squared. So what I do then is I actually do that. I multiply the x times the x and I get x squared. Now usually on the outside we have something else, like it might say x minus 1. Right? Like if it said x minus 1, you'd have to multiply the x by the x and the x by the -1. All right, you'd have to do the multiplication by everything that is outside of your division bar. So on this one then, we have x, and let me erase that piece here. We subtract, just like with long division. X squared minus x squared, that's 0, they cancel. Now again, on this one it ends up not being necessary that we put in the 0x. Generally speaking it would, because we'd have more than just x on the outside. So this 0x actually cancels as well, and then I have a minus 1. Now this negative 1 is a smaller degree than the value on the outside. Does that make sense to everybody? Right, the degree on the outside is a degree of 1. Whoops. There's a degree of 1 here. This one is a degree of 0. Once your degree is too small, then you don't do any more division and you're done. So what does it mean? Well, it means that what you got in the top here, the quotient that came out of it, is your equation of your asymptote. We have an equation at y equal x. That's an equation of an asymptote for us. So I'd like to pause here and actually draw the two asymptotes that I currently have so you can see what this is sort of piecing out to be. One of them is at x equals 0. So x equals 0 is my y-axis. Can you see the dotted green okay from where you guys are? Does it show up okay? All right. And then the other one is the line y equal x. Well, the line y equal x has, let me draw it in yellow, has a intercept at 0, right? Like think about y equal mx plus b. And it has a slope of 1. So you'd go right 1 and up 1 right here. And if you connect those lines, or those dots with a line, that's not good, I'm going to shift it. You'd get the line that looks something like that. That's the line y equal x. So we have our line y equal x, and we have our line x equals 0. That's what the asymptotes give us so far. So this will look different than when we have horizontal asymptotes. All right, we still have to find our x and our y intercepts. So that's our next piece. All right, so my x-intercept is when y equals 0. And that looks like this. 0 equals x squared minus 1 over x. Every time we do this and we attempt to cross multiply, the denominator will disappear. So it will always reduce to the numerator equaling 0. That will always happen when we do this. If I add 1 to the other side, then I have x squared is equal to 1. And when I square root, I get x is equal to positive and negative 1. So what does that mean? Well, x is equal to 1, y is 0. X is equal to negative 1, y is 0. Those are my two x-intercepts. There's two of them. And we'll go plot them. X is equal to 1 and negative 1. That's what I have so far. My next one is my y-intercept. Y-intercept is when x is equal to 0. So I have y equal 0 squared minus 1 over 0. And what do you see happen? Yeah, it's undefined. There's a 0 in the denominator. That's not okay. So what that tells you is that there aren't any. There is no y-intercept, and that should make sense because what's happening along my y-axis? An asymptote. I can't have an intercept and an asymptote on the y-axis. That doesn't work. Occasionally you can on the x-axis, but not on the y-axis. All right, so what does that tell us? Well, I mean, I've got, if you think about my, my slant asymptote, I have a point on either side of the slant asymptote, right? So everybody see that okay? I do have a point on either side of it. So what does that tell me? Well, it tells me that I'm supposed to be getting close to each of those lines. So if I'm going this direction, I'm going to get close up here like that. And I'm going left, I'm going to go, I'm crossing through that, and coming down and getting close over here like this. That's what the right-hand side would look like. The left-hand side is quite similar. I'm swooping up and I'm getting close on the top here, and down and getting close over here. So it almost feels like I took the graphs that I was looking at before and I tilted them, right? That's what it feels like. Those slant asymptotes create what feels like a kind of a slanted looking graph. All right, so how do I find slant asymptotes? I use long division. And I'm only doing that one example to show you the long division, but as you encounter more, if you need help, let somebody know. Success Center, myself, whatever it takes to get those slant asymptotes idea down. There's not a ton of them that show up, but every now and then they show up, okay? Any questions? Okay, so we've done equations and graphing. Now we're going to look at inequalities. So we had done inequalities with polynomials, and this is almost exactly the same. When we did it with polynomials, we factored things. In fact, we did 3 examples this morning you guys had from questions from 3.4, right? We factored things, we set them equal to 0, we create this number line, and we do test points. Everybody agree? That's what we did. We're going to do the exact same thing again. It's just that we'll factor the top and we'll factor the denominator separately. And we'll set up all these pieces that are equal to 0. So on the top, I don't need to set anything, factor anything. It's already in factored or simplified form. So my top is x plus 3 equals 0. That's fine. If you want to factor the denominator, you can. Let's do that this way this time. It does factor. It's a difference of squares. It's x plus 1 and x minus 1. If you just set that denominator equal to 0 and solve, you'll also get the same answers. So you can do it either way. So if we do this, we would have x plus 1 equals 0, and I'll have x minus 1 equals 0. So we would subtract a 3 to get x equal negative 3. Subtract a 1, so x is negative 1. And add a 1, so x is positive 1. There are 3 locations where I get 0 popping up in some of the factors somewhere. That doesn't mean that I actually cross the x-axis at all those points. In fact, I don't. Those points could be places where I cross the x-axis. They also could be places where I have asymptotes, like vertical asymptotes. And they also could be places where I have a hole in the graph, where there was an ability for something to reduce, but now there's a hole. So what we're going to do is we're going to set up that same number line like we saw before. We're going to put those 3 values on our number line, and we're going to test points around them. So putting them in order, I have negative 3, and then negative 1 and 1. And I want points around them. So before negative 3, maybe we pick negative 4. Between negative 3 and negative 1, there's a negative 2. Between negative 1 and 1, there's 0. And after 1 is 2. Again, you don't have to pick those specific values. They're fairly nice ones to choose on this particular one, but you can pick whatever you'd like. And you're going to put it into this inequality. You do need to be a little bit careful. Why do I say that? Well, some of your calculators don't do order of operations the way you might expect that they do. So I would encourage you to find out, is the top positive or negative? Is the bottom positive or negative? Separately, or be super careful with the signs in your calculator as you're entering them. So let's just try one. We have negative 4. So if I put negative 4 and I have negative 4 plus 3 on top, and I have negative 4 squared minus 1 on bottom. The top's negative, right? It's negative 1, but in particular it's negative. The bottom, when I square the 4, negative 4, I get positive 16, and 16 minus 1 would give me a positive. What sign do you get when you divide a negative by a positive? Negative. Thank you so much. You get a negative. All right. And then we go and we repeat the process, and we're now going to do that with a negative 2. So if I do this with a negative 2, what happens? So I'll have negative 2 plus 3 on top. That's actually positive. Negative 2 squared is positive 4. Minus 1 would still give me a positive. So what sign do I get when I divide a positive by a positive? A positive. There's a positive right here. 0 is always nice because it's easy to work with. If I put in 0 everywhere, I get a positive on top and I get a negative on bottom, right? Zeros are good. Positive divided by a negative is a negative. And then we're going to do the same thing with the number 2. Okay, so we have 2 plus 3 on top. That's also positive. And then 2 squared is 4 minus 1 is a positive. So we also get a positive over here. What am I looking for in this problem? Positives or negatives? Positives. And I have it written over here, right? It says greater than or equal to 0. That's positive. So I'm looking for positives. So that's this part and it's this part. Now it does say greater than or equal to 0, right? So I'm going to potentially have some brackets, but you can't just throw brackets on everything. Very much like infinity always has a parenthesis, we need to be careful on this that we have parentheses or brackets based upon whether or not we can actually have that value used. So let me show you what I mean. -3 is fine. -3 makes the top equal to 0, right? And it's totally fine for our numerator to be equal to 0. So I can equal -3. However, if I put in -1, -1 makes the denominator 0, and that's never going to be okay. So even though it says greater than or equal to 0, if I were to use the -1, it makes the denominator 0 and the whole thing undefined. So I still have to use a parenthesis. And the same thing happens over here at +1. I have to use a parenthesis for exactly the same reason. Now, if it bothers you as you're doing it, you could actually set that up that way and make that note sort of on your graph, that those particular points right there, -1 and +1, no matter whether we've got equals to signs or not, have to use parentheses. So if you want to designate that on your graph in some way to remind yourself, you could do that. But this would be our interval on which this is greater than or equal to 0. We are going to do one more of these, but any questions on this specific one? Okay, what do you notice about this problem that's different? Yeah, there's a number on the right-hand side that's not 0. Do you guys see that? That's actually really important. Everything that we do with inequalities hinges on there being a 0 over there. I can't just proceed as normal and pretend like that 3 is a 0 or operate like that. I need to move that 3 to start with. It's got to come over to the other side. So my very first step is to move my 3. So now I have x plus 1 over x minus 2 minus 3. It's greater than 0. Okay. But I'm going to have to now combine those pieces on the left-hand side into a single fraction. So what does that look like? Well, it's not too bad. What I need to do is I need to get common denominators, right? Well, what you can remember is that 3 is the same as 3 over 1. And what I need is the same denominator that's already there. So I can take and multiply the 3 over 1 by x minus 2 over x minus 2. So this gives me x plus 1, and then the -3 is times x minus 2. And my denominator now matches, so I can combine the numerators together. Okay. Again, we've done this before. We did this back in chapter P, but it's definitely been, months at this point since we looked at rational functions and combining them. Okay, so we're going to clean up that numerator. I have x plus 1 minus 3x plus 6 over my x minus 2. So that's a -2x and a positive 7. Oops, I'm running out of space. Let me shift that up. Over x minus 2. So we can't do anything that we did before until we have this set like this. Like that. That's where it has to start. So we got a lot of sort of preemptive work to do on this particular problem, not related to inequalities at all. but simply related to the fact that the form has to be 0 on the left and a single fraction on the right. I said that wrong. 0 on the right and a single fraction on the left in order to proceed. So once we get to that point, we're actually able to start the process that we were doing on the last problem, which is to set things equal to 0. Now, it actually isn't too bad at this point. You'll notice those are both linear, right? There's no factoring that needs to be done. So I'm just going to set the numerator and the denominator independently equal to 0. So negative 2x plus 7 is 0, and x minus 2 is 0. So in the first one, we'll subtract our 7, and then we'll divide by negative 2. You can leave it as x is 7/2, or if you want to change it into a decimal, you can write that as 3.5. Either way would be fine. Over here, we'll add our 2. So x is 2. And these are the values that we will put on our number line. So I have 2, and I'm going to use the decimal. I don't usually do that, so let's do it this time. 3.5. It's on my number line. You can do that as long as the fraction terminates, or as the decimal terminates. So if you got 3.3 repeating, we're not going to do that. You would write it as the fraction that it represented, but with a decimal that stops, you can do that. All right, we need to test points in and around these. Well, before the number 2, there's a 0. I always pick 0 wherever it is. Between 2 and 3.5, 3 is a nice whole value between them, and bigger than 3.5, maybe you pick 4. Totally your choice. All right, so we're going to test each of these, and we're going to test it into the inequality that was the equal 0 part. That's the whole purpose here. We always go back to the part that's greater than 0, whatever stage that was where that occurred. So if I put in 0, I would have negative 2 times 0 plus 7 over 0 plus 2. So I end up with 7 over 2. That's a positive over a positive, which gives me a positive. Now we're going to try the number 3. So I have negative 2 times 3. That's negative 6. Negative 6 plus 7 is actually positive, right? Oh, this is actually a minus on bottom. I made the mistake before then. I'm sorry. That was a sign error here. Over here when I did 0, there should have been a minus 2 on bottom. I apologize. So it was actually positive over negative just a moment ago, which should have given me a negative. I didn't catch that. We'll fix it. Okay, so that should have been a negative when we put in 0. Now we're going to do the 3. So negative 2 times 3 on top is negative 6. Negative 6 plus 7 would give me a positive. And then 3 minus 2 is a positive. So I have a positive for the 3 value. And the next one's 4. So let's put in a 4. Negative 2 times 4 is negative 8. Negative 8 plus 7 would be a negative. 4 minus 2 is a positive. So negative and positive gives me a negative. Which one do I want? Positives or negatives? Positives. This one says greater than 0, so I want positives on this one, which is this interval. Because it says strictly greater than 0, I don't even have to care about whether I can or can't equal things. I automatically get parentheses. So that's actually a friendlier kind of problem than the last one where I had to think about the endpoints. The interval is 2 to 3.5 or 2 to 7/2. Any questions on that? All right, so that one will be due on Thursday.